This is the line spectrum of hydrogen. And we said when electrons in atom of hydrogen, when electron in atom of hydrogens, in hydrogen atoms, they get excited, they come back from excited state to lower state, and they're showing these wavelengths of visible light. So where are these visible lights coming? Well, you're applying energy. There are so many hydrogen atoms. In some hydrogen atoms, electron get excited, goes, let's say this is the first shell, second shell, third shell, fourth shell, and fifth shell. The one which is going to fifth shell, it can drop to fourth shell, so it is releasing the energy in the form of photon, which is red, in the form of certain wavelengths, which has got red color. And there might be some atoms of hydrogen of which their electrons are excited to the third energy level, and they are dropping to first energy level. As you see, there is a larger energy gap between the two, and then you are going to get a higher wavelength, which we see as green. So these different visible colors, they are a result of electrons dropping to lower energy level. So the light, the red light that we are seeing is packages of energy. Its energy is Planck constant times the frequency. This is also, let's say delta E. This energy difference is equal to h nu. H is Planck constant. So nu is the frequency of the light. When frequency changes, wavelengths changes, and when wavelengths changes, we see different colors, depending whether the wavelengths are visible or not. So what are these lines that we are seeing? It is explained here. Suppose you have trillions of hydrogen atoms and much more, and we are applying these hydrogens to energy, electrical energy, high voltage, or thermal energy. We have got electrons at all these levels excited, and then they are coming back. All electrons, Balmer series, are all visible lights, which is emitted. These are all Balmer series. All of them refer to these transition to second energy level. So you have third energy dropping to second energy level, and you have, let's say, n equal to sixth energy level dropping to second, and we can see this. Are there other transitions? Yes. Pascal series. And Pascal series are infrared, we can't see them. How about these transitions? All the electrons at the higher state than first energy. They are all dropping to first energy. They're producing Lyman series. We can't see them because they are ultraviolet. But we can detect these, and we can explain them exactly which transition of electrons, which level electrons are moving, which levels electrons are dropping to which level. So that's our explanation about observation of the line spectrums. So this is the same picture that you observe. It's what we see and what we don't see simply depends on the energy difference between the level of the electron energy. It simply depends where electrons are dropping, which level, and which level dropping into. Which level are they coming from? Which level are they dropping into? Another word, can I say that suppose electrons are dropping from higher energy level to lower energy level? Where dropping into, I call it E final. Where you're dropping from, I call them initial energy level. So the difference of energy between these two is going to result in emitting certain package of light, and every package of light has different amount of energy. Some of them we can see, some of them we cannot. So if I'm going to go on further, if electrons are dropping from second energy level to first energy level, so initial location is, I call it Ni, final location is Nf. We also said that Bohr came up with a mathematical equation to calculate energy of electrons at different levels. He says energy of each main shell is related to this formula. RH is a constant. By doing complicated mathematical formula, he came up with the value of R as well. So each one of these energy levels have certain energy which depends on the principal quantum number, the value of n. The term is the energy of level. Is it n equal to 2? Or is it n equal to 3? Or is it n equal to 4? So I raise the principal quantum number by a factor of 2 on the bottom of ratio, and I use the value of the constant, RH, right? Constant, I can calculate the energy difference between any two levels. I can calculate this energy. And once I calculated energy, I can calculate the frequency of the light. Once I have the frequency of the light, I have wavelengths of the light. Then I know whether it is visible or not. And if it is visible, is it red or green? So energy released when an electron is dropping from initial energy level of an I to an F can be calculated by this formula. And this is only for hydrogen atom. It's a very simplified case. And again, if electrons are dropping from the third level to first energy level, your Ni is equal to 3. So how do I write this formula? I enter 3 here. 3 squared, which is 9. And if it is dropping to n equal to 1, Nf is 1 squared. And I have the value of this constant. Then this is the constant. This is the value of the constant. 2.18 times 10 to minus 18 joule. So I can actually predict the color of the light which is emitted simply by knowing which shell is it dropping from, which shell is it dropping to. All I need to know is Ni and Nf. And you know N is always it's always an integer. It's either 1, 2, 3, 4, 5, 6, and so on. So once I calculate the energy spacing between the two levels where electron is moving, This is Planck constant. We have the value of Planck constant. This is the speed of light. We have that. Then we can calculate the wavelengths. Once we calculate wavelengths, we go back and look at the line spectrum. And if we observe exactly the line spectrum, the wavelengths that we saw from line spectrum, then we know our formulas are correct. And actually, the hydrogen line spectrum was exactly the wavelengths which was obtained by these formulas. We're doing a lab pretty soon. Inside your lab, instead of using an I, you will find the formula there is not an I, and we use N of M, or we use actually M. So in the formula that you use for the lab, M stands for initial energy level, where electrons are dropping from. N shows final level they are dropping to. So instead of N2, we write, instead of Ni2, we write M2. Instead of NF, we write N2. This is just to make sure we can confuse you. Otherwise, it would be too boring for you if we use the same letter system. We're trying to impress you by changing the letters on you. Anyway, so if you want to find the wavelength of emitted light, you use this formula. This is not the same as RH. This is a different constant because it's a constant which is including Planck constant and the speed of light. But we give you the value of that. This is the value of R constant inside this new confusing formula. But the students have done these calculations simply before, and I bet you can even do a better job. All right.